Hi, my name's Chloe. I work with Delta T Refrigeration. You may also know me as the Cooling Girl on Instagram. And I've been a refrigeration engineer for 2 years. I'm really passionate about developing my skills in the RACHP industry. And today we're going to be replacing a compressor, capillary and dryer on this small multi-deck fridge. The first thing I do is check the refrigerant within this system, which is R452A, and it has a system charge of 1.3 kilos. We found the fuse on this unit to be repeatedly blowing in the plug, and after checking the relay, capacitors, fans and heater bars, it was evident that it was the compressor that required replacement. So without further ado, I disconnected the condenser fans and compressor supply, taking note of exactly where each connection went, to ensure that I put them back in the correct place. Here we can see an overview of what we're going to change. So the compressor, the dryer and the capillary. The capillary follows the suction line up into the side of the fridge on the right hand side, where we can see here that it connects to the evaporator. Step 1, safety first. Safety glasses on, gloves on. I remove the core from the only Schrader valve present on the system, and this removes the restriction and speeds up the recovery process. After connecting my manifold to the system, I can see there's 8.9 bar of pressure. I connect my manifold to the inlet port on my recovery machine, and then another hose goes from the outlet port to the recovery cylinder. Ensuring my recovery machine is set to recover, I first purge the lines to remove air and moisture and preventing contamination from entering the cylinder. I carried out the recovery of the refrigerant from this system using certified recovery equipment in full compliance with F-gas regulation. This ensures environmental protection and adherence to legal and safety standards. Once the recovery machine had removed the refrigerant from within the system, I used the self-purge function on my recovery machine to remove residual refrigerant vapours from the machine's internal components and hoses. This prevents cross-contamination, reduces environmental impact which might arise from accidentally venting off the refrigerant during disconnection, and it protects the recovery equipment by removing the refrigerant and moisture that could otherwise corrode and damage internal components. We found that the pressure within the system rose slightly during that self-purge, so we repeated the process to ensure that every last gram of refrigerant that we could remove from that system was removed. With the system safely emptied, I can now move on to removing the faulty compressor. So using a pipe cutter, I cut the discharge line and the suction line at the appropriate positions. As we can see from many joins in the suction line, this compressor has experienced leaks on its pipework before. This was also evident as an oily residue existed around the base of the compressor. Removing capillary lines can be very dangerous and takes great care. Fortunately, these ones weren't brazed in too deep into the evaporator and we were able to remove them. We consider it essential to replace the dryer as we've opened up the system, and certainly due to the nature of this system's fault. Whilst making up the new pipework for the compressor, deburring is essential after cutting copper tube. Burrs can disrupt refrigerant flow, making the system less efficient. Ensuring the copper swarfs are removed from inside the pipework is critical too, as capillary systems are very vulnerable to blockages. With the fire extinguisher close by and my heat-resistant gloves on, it was time to get brazing. Using oxygen-free nitrogen to prevent oxidation inside the pipework, I'm using my copper filler rod, as there are no dissimilar metals here. I have wet rags around the body of the compressor and on the floor, just in case any material drops. Wet rags act as a great heat sink to protect the compressor from any heat damage. I brazed most of the pipework into position whilst the compressor was in an accessible open space, This was the safest way. It left only 2 connections to braze once the compressor was put back into position. After measuring the old capillary at 66 inches, it was time to cut the new one to size. I used special capillary cutters to ensure the tiny tubes were cut at an angle, preventing the cut from crushing the ends of the pipe. Once everything had cooled down and was visually inspected, it was time for a pressure leak test. First, I pressurised the system with 5 bar of oxygen-free nitrogen. I found many obvious leaks at this pressure, which saves time, nitrogen, and it's much safer than the final test pressures. Next, I undertake my strength test, generating my PS value from the EN378 Part 2 specified design temperatures table. Here you can read my calculations for my strength and tightness test pressures. Starting at 26.5 bar, the strength test was a success. Then onto the tightness test at 24 bar. I make my way around each and every joint here and spray it with bubble up leak detector, and I visually inspect with my mirror. Now I'm confident the system is leak free. I connect my vac pump and evacuate the system down to 2000 microns. This removes air and moisture, which could otherwise cause system issues like acid formation and inefficiency. With a fresh charge of vac pump oil, we're good to go. In the first few minutes, it was clear the contaminants were in the system, so we changed the vac oil and kept our eye keenly on the condition of the new charge. We connected the torque gauge to the newly brazed in high side trader to make sure that we were calculating the vacuum from the furthest point in the system from the vacuum pump. The hold test showed the vacuum did not increase by 2% of the vac achieved, so it was time to recharge and electronic leak check this system. As R452A is a zeotrope, it's charged as a liquid to maintain its design composition. It's charged directly into the high side to prevent liquid from entering the suction side of the compressor. So I charge 1.3 kilos into the system, as we saw from the data plate at the start of the video, and we can see it's reaching all parts of the system, travelling through the capillary. Next, I leak check all accessible joints on the system. I allow the electronic leak detector to warm up in a location free from refrigerant away from the system. And with no leaks identified, it's time for the moment of truth. Here I'm reconnecting the incoming power supply to the condenser fans and compressor. Despite having confidence in my process of refrigeration, I'm always so nervous to finally switch the fridge on, but luckily it booted straight up. I checked the compressor running current of 7.94 amps. Both condenser fans were working and the air on, air off and evaporator probes were reading the correct temperatures. With sufficient suction superheat and subcool, the fridge hit set point in no time at all. And frankly, I was elated. Next, we initiated a manual defrost and ensured the heater bars were operating. And by checking parameter 44, defrost termination temperature within the controller, it was clear the evaporator probe must read 12 degrees C before the defrost would terminate. Now that was a long old night and I was very much ready for bed come home time at 5:33. I'm now going to show you some of the electrical tests we undertook on site before we removed the compressor. Using my digital multimeter set to ohms, I measured resistance between the common start and run terminals. The results showed there was no open circuits or shorts to ground. I then undertook an insulation resistance test. I set the tester to 500 volts and I connected one lead to the compressor terminal and the other to earth. The results were in the gigaohms. There was no insulation breakdown or moisture ingress. Next, I set my multimeter to the capacitance setting. The start capacitor was within its rated microfarad range, but the run capacitor failed. Despite changing this capacitor and the relay on site, it did not fix the issue. So we put this down to a mechanical failure. That's a successful compressor replacement. It's another step forward in my career as a refrigeration engineer. Thanks for watching my Women in Cooling competition entry. I'm Chloe-Jennings. You can follow me on Instagram at thecoolinggirl, and I'm so proud to be part of this incredible industry.